All right. So yesterday we started our lesson on building muscle. So we worked the pecs and these muscles here is a cutaway, and also muscles in the back and the arms and biceps.
Wow.
Ooh, that was interesting. Is anyone sore today?
Yes.
Oh, slow,
Yes.
slow.
Did you? Because we did a lot of push-ups yesterday.
60,
I'm a little
at
bit
least
sore.
60.
Yeah, we did 60. But if you're sore,
I'm a
Yeah.
little bit sore in my
No, I'm
pecs a
not.
little bit.
No, not
I'm
as
only
much
sore
as
because
before.
I did a little more at home. But
I'm actually sore at my
I'm not sore
triceps,
from
my
what we did
biceps,
here.
and,
So.
okay. I just want to show that there are a lot of muscles here, and we're learning the
and my abdomens and.
Where's the vertebrae?
vertebrae back here.
Okay.
But we'd have to dissect it. That's hard to do with this. Anyway, we're going to talk about how these muscles work. So, first, I think we talked some about myosin and actin yesterday.
Yeah.
So this is what they look like. There's a ribbon image, and this is what it's going to look like in Fold.it. But this is what it really
That's
looks like as a
basically what
blob.
cells are made up of.
Yeah, these are all atoms. These little blobs are all atoms. But they show it as a ribbon structure here. Do you see?
Okay.
Which those are atoms?
These are atoms, but
So-
it's
so
colored
this
in
is
like
really tiny.
Yeah. First, as an introduction, we're going to watch this video to kind of explain what's happening and then review it.
Muscle myosin is a dimer with two motor heads that act independently.
Fine, good.
Each myosin head has a catalytic core and an attached lever arm.
So this is
A coiled coil rod ties the two heads together and tethers them to the thick filament seen on
the
top.
actin.
The helical actin filament is shown at the bottom.
Oh, okay.
In the beginning of the movie, the myosin heads contain bound ADP and phosphate and have weak affinity for actin. Once one of the heads docks properly onto an actin subunit, phosphate is released. Phosphate release strengthens the binding of the myosin head to actin and also triggers the force-generating power stroke that moves the actin filament. ADP then dissociates, and ATP binds to the empty nucleotide binding site, causing the myosin head to detach from the actin filament.
Oh, so they're actually attached.
On the detached head,
They attach.
ATP is hydrolyzed, which recocks the lever arm back to its pre-stroke state. Thus, like a spring, the arm stores the energy released by ATP hydrolysis, and the cycle can repeat.
So, couldn't you theoretically...
The actin filament does
this,
not
like,
slide back after being released by the motor head, because there are
It's sort
many
of like
other
a
myosin
perpetual
molecules
energy,
also
like,
attached
it
to
could
it,
just be reused.
holding it under tension.
ATP could connect to the other phosphate. Create another ATP.
The swing of the lever arm can be directly observed on single myosin molecules,
This is
here
actual
visualized
footage,
by high-speed
of
atomic
protein,
force
which
microscopy.
is ridiculous.
Must be really small.
Yeah, this is amazing technology they use here.
Oh, so when you see it, it's like in the line in the middle.
The hip
You start making like
Wait,
a
this
triangle.
makes up
goes
muscle.
like this.
Yeah. So
exactly.
this is how your muscles work. Imagine this thing here is your arm, and if this is zoomed up, this thing triggers. You know when it's where does the action happen?
When it fits into the...
When it fits in.
Wait, I thought it was just that your bones get stronger. Is that?
No, it's your muscles.
Yeah, your muscles.
This is how you move your muscles. When did the action happen, and how did it happen?
This happens so fast.
Wait, so over here on the bicep, is that a muscle?
Yes.
Yeah.
This is a
Or
muscle.
is that a bone?
And there,
This is
right
It's like
there,
a bone.
It's
There's a bone under it.
Both.
all this these are attached to tendons which move the muscle. But where is the action that pushes it? Right there.
The arm stores the energy released by ATP hydrolysis, and the cycle can repeat. The actin
So right here, this is what we were talking about yesterday. But this protein is now cocked.
Yeah.
Like if my arm's out like this, you could say, imagine the proteins
Like a
shaped like
spring,
this
and then-
are cocked. And they're cocked with ATP. And remind where is ATP made?
In the...
Yeah.
ribosome, yeah. I mean, no,
No.
in the...
Mitochondria
Mitochondria.
and in the cytoplasm. And then when it goes like this, the ATP releases a phosphate and becomes ADP, and we talk about the ATP to ADP. That's how energy is created. So here it's being used by this protein for a spring action, and that spring action happening billions of times when I do this is what pulls the muscle and constricts my muscle.
Oh yeah, like so in when they try to get people taller or stronger, so when they keep on like when they stretch it out, it somehow gets stronger as like it like grows kind of.
Well, the strength comes from how many of these you would have in a muscle, and if you work out more, you get more of these. You'll have more muscle cells. That's when you get larger muscles. You have more of these things working together. Instead of a billion, maybe you have 100 billion. But I want to talk about this shape changing.
If I would move my arm, just keep on moving it like tons of times, maybe for like as long as I could, I'll get stronger that way. Just not as fast as maybe doing a push-up or something.
Yeah, I mean,
Yeah.
but you're still doing the mechanism. But what's the protein? The protein. Think of the protein.
You gotta eat
Myosin and actin.
muscles too.
I'm gonna load
Some
a
push-ups are faster though.
just a random protein. This is not myosin or actin.
You know, there's an eraser in there.
Yeah, but just remember that we do want to remember the ATP. And ATP. So this is going to be a complicated protein.
Whoa.
Saul, do you understand?
So what are those brown?
Well, first there's some things I want to bring up. We've talked about these before.
Yeah.
This is an empty void. Pack the protein to fill the void. So we want to, avoid voids.
Honey.
But then also there are those star things, and now we've created a lot of voids.
That means that they're touching.
Clash between two atoms. Now there's actually something I want to show you that I forgot to bring up.
No.
I want molecule shapes. I want to run this.
Saul, pay attention.
Okay.
All
All right. So here is a molecule.
Yeah.
Notice I can't get the atoms to touch. Atoms repel. If atoms get too close,
No, what if you
What
do it really
happens?
fast?
Oh yeah, like a magnet.
They
well, I can
repel.
try to do it really fast.
Right.
And there's actually even better animation over here. General chemistry, it's on atomic interactions. This also kind of explains why there's all this wiggling in part. Here comes.
Wait, so are we recording the whole class?
Okay.
It's okay.
So if we play this, there's a force, and if the atoms get too close, they repel each other. So atoms touching, what's this? These are the electrons.
Yeah.
If they get too close, that's what those stars mean here. So what's going on right here?
No,
When they get
what
too
happens
close.
if they touch?
Well, they kind of bounce back and forth because there is this kind of odd attractive force. But when atoms get too close, they really repel each other. So that's what's going on. What's that
So they're
symbol means?
opposite. So when they
There's
when
two
they're
that are
like that,
that are touching.
so they're still able to touch each other. Just they always repel.
And
Like a magnet, you could still make it touch.
Yeah, but
Just
they
it-
push the other way
Yeah,
very
there's
hard.
so much pressure.
And that's what's going on right there. That's what's happening. So we'll wiggle this to get it.
Shaking.
Let me just move some things out of the way.
This is epic music.
So we have a lot of voids, and I mean, let's just shake it. That's sort of something reasonable. All right, so this doesn't really look much like the protein we're talking about, but there is some similarity in that we do have a chain here, and imagine this is the arm that moves up and down, because this is the spring action. So imagine right now, this is it cocked, and then it would release, push forward, and that would be the muscle movement.
I see.
But how does that affect, you think, the stability of the protein or the score? That movement.
The movement? Well,
Yeah.
at first it lowers it.
Well,
it raises
lowering
it.
it could build.
Because it's making, it's filling voids, or it could be, and clearing crashes or creating crashes.
Yeah, when that arm moves, it could really be creating voids, or it could be creating these clashes.
But then it moves back to its original position.
It moves back to original position when what gets back into it? Remember the ATP and the ATP?
Yeah, that's true.
When the ATP is there, for some reason it prefers a state, and again, this is artificial. It scores 0. And then when the ATP releases, it does that. So is that a process that takes energy to move that?
Yeah.
Yes, and that's what it uses the ATP for. The ATP was used to make that swinging movement of this kind of arm of the protein to push on the actin.
I see.
And then when after it attaches and the phosphate comes back onto it, which is the hydrolyzing, it moves back to its original position.
Epic music.
Let's look at another protein. Maybe there's one that's seem a little more similar. Let's look at something basic. Closing the gaps. So it is.
Oh, this is what we did.
This is kind of similar, and we've done this, and we can actually show all kinds of. Oh, this one doesn't let you show all the possible meshes. But here again, this is an arm swinging, and that creates a giant void here. It'll give me a good score, but.
You mean if you just keep on moving it, it'll get you a better score?
Well, having it in the least energy state. The thing is, a movement like that would take energy. So now there's a problem of a void there. That's what that symbol means. And what does the symbol mean again?
A clash.
It's a clash, just like what's going on here. Just atoms getting too close.
Wait.
But let's annotate. So this, if this were myosin, this force here would be the arm of it moving outward, and what is it moving? So the arm. What does it push on?
CD.
The arm pushes the actin.
CD.
Better to just use regular marker. The arm pushes the actin. So someone come try.
Yeah, me.
Okay, over here.
I try.
But explain this as if explain this as if it were
Stand up.
the
So
what we're talking
basically,
about.
so the myosin would spring
Is
back.
it right now? Is it cocked or not?
Right now it's
It is not cocked.
not. It would be
What makes you
cocked
say that?
Because it's not. Because when it's attached to in actin, it's more like separated from the other one. It's more pushed. Because you can't only do it on this because they move like this. The other one would move like that.
Show me. Well, show me what you mean with this.
Okay.
Right now we have voids, which
Like it would move more like that. No, not out. Like. How do you do it on this? Here, let me see.
Hey,
You wanna
you're just
load-
messing it up, Moshe.
do you want to load a different protein that maybe would
Spread it out
look more
more.
similar?
Do you understand what I'm saying? It's like instead of it going like this, myosin would go like this.
That's true.
So that's why this is a little bit hard to do it on. So, but when it was cocked, it would be like this, and then it would fling up.
Yeah, well, it was close together when it had the ATP, and when it released the ATP, it did that pushing motion.
Yeah.
It swung the arm out.
Okay. So the cock position was when it was like this.
Yeah, that was when
Okay,
it was tied
fine.
together.
So then in this, it would be this was a cock position, and
But
then once it released
let's
the ATP,
assume this was.
So it would be cocked in this position.
Yeah.
How's that cocked? No.
Well, the thing is, there's right now.
No,
if
like
this
when
were,
when it's your arm, it's like out like that, but it's like this.
yeah, don't think of this as your arm. This is just
I
something.
mean, it's
that's
like it's
gonna,
after it was.
imagine
after
this
you
is
moved
gonna-
the sprint.
This is going to push on something that pushes your arm forward.
Okay.
That's kind of how you should imagine it.
I see.
But right now, there's somewhere over here. There's a binding site where there's ATP.
All right, so if
And
that.
when ATP is there, there's energy stored, and then there's a binding site when it touches the actin.
It's like down there.
We'll just say the actin's here. When it touches it,
Then
this
it
ATP
releases
a phosphate, and then what happens? Please move it.
and then it
Pushes the actin, and that causes the muscle to move.
Yeah, and then
But what are some possible things here? Is this a void here?
yes.
Yes.
Yeah, it's not showing on the score isn't going down, so maybe this is not a void that is bad based on
Yeah.
whatever properties this protein has. But you understand, it's not clear. It's clear that whether this is a ATP or ADP makes a big difference on the preferential state of this part here.
Yeah.
Because I don't know which is has more
Alright,
classes.
so
or-
Mr. Reynolds, so if you would make that go straight totally, what would that be called?
Straight.
Why don't you spread it out more?
Yeah, you spread out both parts all the way.
Well, there's clashes and voids up there now.
What on the top?
Yeah.
Shake it.
See it over there?
Shake it.
Yeah.
Not
shake
here. I
it.
said they move it back. It's gone.
Nice.
And
We almost won.
You can just shake it and then win.
No, just move one of those red things. The other one. Yeah, nice.
You're probably this one.
Yeah, it's saying
Nice.
the helices are too far apart. These are the helices,
Okay.
they're spinning like a
That's
helicopter.
good. That's good. Leave it.
Good, perfect.
Up.
Make it more void.
Getting close. I'm getting close.
There.
No.
Just stop it and wiggle, because the side chain wigglings. Stop it, and I'll hit W for you.
Awesome. Try one more time.
Or go to actions. You have to click there and shake.
Shake.
That's just gonna let you do. I guess that was not helpful. So stop it, move it a little bit, and check the side chains again.
I see, but if I close the voids.
Just try resetting, just because it's complaining.
Okay, there you
First, just start by shaking the side chains.
go. Right.
And proteins want to be as collapsed as possible.
Oh, okay.
So if you can kind of visualize that these are already looks pretty good, that it's parallel. Right
So
here.
the most is gonna shake. So let's just move that.
No, move that circle one on the side.
Yeah, move the circle one, please.
There?
Yeah, that one. Move it
No,
up.
it's gonna clash.
That's nice. You do it.
It's just -3.
My bad.
All right.
The blue one.
I tried.
Top blue one.
Yeah, I'm just gonna go back to the video. We can solve this puzzle after that, but I want to go back to the video. So if you can move the way, so I can get back to the YouTube video we're watching.
Sponsored by you. SDK.
And see if this makes more sense now. Because if this makes more sense,
that act independently.
so
Each myosin
Yeah,
head
think how it's
has a
folded this
catalytic
way.
core
Yeah.
and an attached lever arm.
and that is the
A
ideal
coiled coil rod ties the two heads
shape
together
of it.
and tethers them to the thick filament seen on top.
But as you see,
The helical
the
actin
shape of
filament
it
is shown at the bottom.
can cause all kinds of
In the
problems.
beginning of the movie, the myosin heads contain bound
Isn't there
ADP
some, like-
and phosphate
Like
and have
disease or
weak
something that
affinity
changes,
for actin.
like it's like not bound right or something.
Once one of the heads docks properly
Is there
onto
some
an
way to,
actin
like, is there
subunit,
some disease or something that
phosphate
stops it
is
from
released.
actually
Phosphate release strengthens the binding of the myosin head to actin and also triggers the force-generating power stroke that moves the actin filament. ADP then dissociates, and ATP.
Okay, so let's start right there. Is it possible that would? I mean, if I were playing the game, I would imagine could that create a void there?
Yes.
Yeah.
Maybe. I mean, clearly this happens in nature, so clearly this
Actually,
is
it
a thing.
depends on the protein. I mean, it's probably farther apart than it looks. Like in the game, you know, when it's a little farther, there's a void. Other way, there's no void. Once it's closer, there is a void. So maybe it's the distance is different.
It's possible. It could be a void. It could be not.
It sure could. I mean, this took energy. Something that takes energy means this might not be the minimum. This is not the minimal energy state. So this would probably get less points than if it were in, tighter, because this took energy.
It takes a lot.
It takes energy. Yeah. But it is attached and there are different things on it, so it's complicated. But that's a reasonable thing to say, I think, that this could be a less stable state, but it is less stable because it took energy to do it. And when you, like pushing a ball up a hill, it takes energy. But then it rolls back down, which is a more stable state.
P binds to the empty nucleotide binding site, causing the myosin head to detach from the actin filament. On the detached head, ATP is hydrolyzed, which recocks the lever arm back to its pre-stroke state.
And when it's clumped together, that just looks like a better
Thus,
protein.
like a spring, the arm stores the energy released by ATP hydrolysis,
Muscles are
and
really
the cycle can repeat.
Is there an opposite where mu is
Muscles
that?
are very cool.
The actin filament does not slide
well, if you
back
look at it
after
from
being
Actin's
released by the
perspective, you
motor
can think of
head,
it that
because
thing
there
as
are many other myosin molecules
can think of it
also
either way.
attached to it, holding it under tension. The
And
swing of the
just to
lever
get back
arm can be
to
observed on
one
single
other little video to show you, which is here's a really cool video about that shows the protein folding properly. Here we go. So these are the amino acids.
Who made up these letters?
I don't know. So that's space filling model. That's what the
really-
It's a
atoms
bunch
look
of
like.
mumble jumble.
Letters. It's a really nice.
Now they're gonna make it look like there's still a space filling. See how it's kind of getting more compacted
Yeah.
and it's solving itself? So that's solved.
That's what it looks like.
Yeah. Now it's going to show it it's showing the amino acids again. And then it's going to show it.